Hello students, this is Dr. Ben. I'd like to work through a problem out of Chapter 8 that has to do with rotational equilibrium applied to the human body. So here we have a situation where a person is standing on the ball of their foot, and we see some of the internal structure of the body, the bones and the muscles here. And we're given some information about the geometry and the various forces that are acting, and we want to figure out some information about two of the forces in particular. One being the force that the Achilles tendon exerts on the foot, and the second being the force that the tibia exerts on the ankle. Alright, so even though this is a two-dimensional problem, it seems like a good strategy to model the foot as a rectangular object, kind of a beam or a boom like we had in several other problems. And I drew that on the right of the pictorial representation, and I indicated the three forces that are acting, and the pivot point is this spot that is where the tibia touches the ankle bone. So it's basically a balancing kind of a problem that has to do with rotational equilibrium, and so we would set the net torque on the ankle equal to 0. And of the three forces that act, only two of them cause torques, because the lever arm due to the force the tibia exerts on the ankle is equal to 0 because it acts at the pivot. So the torque produced by the Achilles tendon plus the torque that's produced by the normal force will have to add up to 0. Alright, the Achilles tendon is going to cause the foot to rotate clockwise, so its torque would be negative the value of that force, F sub A, times the distance that that force is from the pivot point, 0.046 meters, times the sine of 90 degrees. And then the normal force, which is on the other side of the fulcrum, the force is N, symbol, it has a value of 750 newtons, times the distance, 0.128 meters, times the sine of 90 degrees, and all that equals 0. So we can simply solve this expression for F sub A. So we're going to get the normal force times 0.128 divided by 0.046. And we put that into our calculator. 750 times 0.128 divided by 0.046. That equals 2090 newtons. So that's a pretty big force. That's the force that the Achilles tendon exerts on the foot in order to raise the foot up, as this diagram shows. Alright, so in order to do the second part of the problem, in order to find the force that the tibia exerts on the ankle, because that force occurs at the axis of rotation, we can't use torque methods, so we need to use force methods and apply the equilibrium condition. So if we use Newton's first law in the y direction, we would have that the force that the Achilles tendon exerts minus the force that the tibia exerts plus the normal force equals 0. So if I solve this for the tibia's force, I'll get F sub A plus N. So I'll take my answer and add 750 to it. So I have 2090 plus 750. So that equals 2,840 newtons. So both of those forces are pretty large, partially because the distances involved are small, but partially because of the size of the normal force that we were given, 750 newtons.